All right, in this video, this is actually the first of a series of videos where we will talk about and explore the use of terms such as energy, work, and power. Now, it's important to recognize that uh, it's very common in biomechanics to take what we call a Newtonian approach to solving problems, solving physics problems, or solving problems of movement, or doing an analysis. And all the Newtonian approach means is we're going to use Newton's three laws of motion to understand the forces causing motion and the resulting motion. So an object stays at rest unless a force causes a change in motion. First law, second law, F equals ma in a quick summary. And third law, for every force, there's an equal and opposite force. Every force acting on an object, an equal and opposite force created by an object. Using those three laws, we can attack a lot of problems, and they become very straightforward in terms of how to approach understanding movement. But there's other ways to solve physics problems and problems of movement, and one way that we'll talk about now is using energy as a concept. Now, energy just as I said, it's a concept. In fact, it's really a set of math rules that work well, because they work. It's really a set of mathematical equations, and we use those equations in a way that we still ultimately understand movement. So it's a different approach, and it's an important approach because we drink energy drinks, we eat energy in terms of food. We do workouts. We go to work. We use terms like aerobic power and anaerobic power. And so it's really uh, important to understand these three terms, energy, work, and power, and how they're related to each other. And ultimately, what new information they provide to us versus taking a Newtonian approach to understanding movement. All right, so this is a series of presentations on this, and I'll start with this one, which we're just giving a big overview of energy, work, and power. Now, I often say work, energy, power, but I'll present it in this order. So my title slide is Energy is the Concept, Work, and Power. Now, some other terms that we'll start using and already do use are speed, endurance, strength, work, energy, and power. So the last three is what I really want to focus on. But the first three are terms that are ultimately going to be related back to the work, energy, power concepts. All right, so speed is simply the ability to achieve high velocity. We can talk about running speed, biking speed, swim speed, any of that. Speed strength is a sort of a subset term used. It's force developed rapidly or at high velocities. So now this is a term that would be used more in a strength training type of environment. And speed endurance is the maintenance of maximal velocity over a period of time or in multiple bouts. So this would also be analogous to a term that we would use, which would be fatigue resistant. And I use fatigue resistant a little bit more in 457, 657, where we go through the ability to sustain a pace over a long period of time. All right, so now endurance is simply, if we look up in Taber's Medical Dictionary, the ability to withstand extraordinary mental or physical stress for a prolonged period of time. So extraordinary. Or if we look up in just a general dictionary, Webster's or what have you, the ability to continue despite pain, fatigue, and stress. So this class is focused on endurance performance. And so we are really interested in the ability to continue to exercise or the ability to sustain a pace despite any pain that we may be experiencing or any fatigue, it's a whole, that fatigue is a whole nother term we need to define and talk about. But we can just think of fatigue right now as a general tiredness or despite the stress placed on a system. So the ability to continue. And there's a lot of factors going into that ability. Okay, so human performance, and I've used this model before, and this is a really important model to understand when we start trying to pull in information from different areas in kinesiology. Human performance is basically the ability to take chemical energy in the body, or carbohydrates, fats, proteins, and transform that chemical energy to mechanical energy or movement. All right. And we transform that energy from in a carbohydrate aerobically or anaerobically over to mechanical energy. And mechanical energy for right now, we can just think of as movement. And even more specifically, when we think of this ability of the body to develop useful mechanical energy. And that ends up being something that we need to start thinking about is neuromuscular coordination, or co-ordering, ordering things in a particular way so that we have a useful mechanical energy to cause movement. So this really involves generating the right forces and the right magnitude of force and the force is applied in the right direction and also at the right moment in time. So there's a lot of coordination of muscles generating forces in the body. And you've learned about agonist, antagonist, those types of actions, neutralizer, stabilizer, all that. This is all coordination, trying to generate. So it's not as simple as chemical energy being transformed to mechanical energy and we have performance. We need to coordinate all that mechanical energy in a particular way so that we have a good performance, right? But the bottom line of having human performance is we are transforming energy from one form to another. So it behooves us, it really is on us to understand this concept of energy. So let's go through it a little bit more. Energy, the definition of energy, the capacity to do work. Now, we haven't defined work yet, but we'll do that in the next presentation. But work is simply a force applied over some distance, okay? I have to apply a force and I have to have some movement. If I don't have either one of those, I don't have any work being done. Now, I should say that I'm going to take a very mechanical approach to explaining these concepts of energy, work, and power versus a physiological work. And we'll merge those two areas in a little bit because we're talking eventually about rate of oxygen consumption, amount of oxygen consumed, and those will actually be analogous to our terms that we're talking about here in the mechanical world because they represent aerobic power or aerobic work being done. All right, so energy is the capacity to do work. It's the capacity to apply force over some distance. The units of energy are joules. The formula of energy depends on the type of energy we're actually talking about. Nuclear, heat, mechanical, chemical, light, electrical, what have you. There's all different forms of energy. There's all different capacities to do work. This is where it gets a little confusing, but this is why the math of energy actually works because it works. And I know that sounds silly, but it's a set of math rules that we're going to follow. So energy concepts, sort of thinking of how we use this term. Energy is needed to get an object moving, or what we'll learn is a better way to say that work needs to be done on the object, okay? That's a better way to say that first bullet. You know, I'm tired. I don't have a lot of energy. You know, word on the street type phrases like that. Um, I don't have a lot of capacity to do work, and work needs to be done on the object. A force needs to be applied on the object, and so that the object can move in some distance. Energy needs to be dissipated to slow an object down. Right? This is something that we will talk about, especially with running shoes. Work is done by the object on something else, causing that something else to slow down. The shoe is doing work on the person to slow the person's downward movement. So energy is being dissipated, is what we would say in a layman phrase, to slow the person from moving downwards. We may say energy absorption. Right? We're actually finding that that's not actually a correct thing to say, but it's understood what we're trying to say, or I guess if we can understand the math behind phrases like energy generating or energy absorption, then we'll be in a good spot. A couple of examples: shot put. The athlete performs work on the shot. That's the object that they're actually throwing, if you will, and the object then gets projected off into the air. Catching a shot put, the shot performs work on the catcher, and the catcher absorbs the energy. The catcher stops the shot from moving. Not that you would try to catch that object, actually would have a lot of energy, a lot of capacity to do work, which means you need to apply a lot of force to stop that shot from moving. All right, so let's keep moving. Conservation of energy. This is a really important concept. Energy cannot be created nor destroyed. Okay, it cannot be created or destroyed. You cannot create energy. You cannot destroy energy, but you can change it from one form to another. Okay, remember I stated earlier there's all different forms of energy. Well, that transformation of energy from one form to another is really the basis of using energy to solve movement problems. Now, I guess you could start thinking philosophically, well, if energy can't be created or destroyed, how did the universe ever get created? But that's a whole nother topic. All right. But we do have this concept, this math concept, that energy cannot be created or destroyed. So E1 equals E2. That means if we know all the energy at moment one, that energy will be the same amount as in time two. However, it's important that the energy at time one is not necessarily the same energy as time two. That is, given the example I've already introduced, maybe E1 is chemical energy, and maybe E2 is mechanical energy. Now, what's interesting, when we start going down that path, there's a more general form of that equation indicating that we hardly ever can add up all the amounts of energy at time one and all the amounts of energy at time two. So sometimes we limit ourselves to types of energy that we're going to try to measure. For example, chemical and mechanical. But it's never a perfect transformation of energy from one form to another. Often energy goes off into some other form. For example, heat. So a lot of times we'll write a more general form if we know all the energy, well, if we know the chemical and mechanical energy at time one, and then we measure the chemical and mechanical energy at time two, they won't be equal to each other because there may have been some transformation to other types of energy, for example, heat. And so we would just add this Q factor into our math equation. Again, energy is a math concept. And so we would balance our equation, say, okay, we measured all the chemical and mechanical energy at time one. We measured all the chemical and mechanical energy at time two. Wasn't perfect, so we'll just add in a Q factor representing the other forms of energy that may have been created. And in the body, we know that that's heat, and so as we start exercising, we transform glucose and fats to mechanical energy ultimately, but it's not 100% efficient. We're not transforming all the energy from glucose and fats to mechanical energy. And that's where we heat up during exercise. We get warmer and then we sweat and what have you. Okay, now this is a simple example illustrating the transformation of energy from one form to another, and it's projectile motion. And we can do all our projectile motion equations or understanding of the movement based upon energy. And what I have here is just this object being dropped. I guess that's the easiest way to look at it. It could also be going upwards, but I just need to set the stage a little bit. And at the highest point, and I haven't introduced these types of energy yet, but I will soon. We have potential energy, which is one form of energy, one form of mechanical energy. And then at the lowest point, we have another type of energy, kinetic energy. And as this object moves from this position down to this position, the energy is going to transform from potential energy to kinetic energy. It's going to transform based upon this equation, mass times acceleration due to the force of gravity times the height of the object. And as that object gets lower, that height reduces, and ultimately getting to zero. But as this object starts to move downward, we know the velocity speeds up and the amount of kinetic energy increases based upon this equation, 1/2 mass times velocity squared. So by the time that at this moment where the object is dropped, the initial velocity is zero, there's no kinetic energy, lots of potential energy. As it moves downward, the potential energy decreases and the kinetic energy increases. The total amount of energy remains the same in the system. That's conservation of energy. And that's just using mechanical energy as an example versus my other example of chemical and mechanical energy. Okay, quick summary. Conservation of energy, the total amount of energy at any moment in time is the same as the total amount of energy at some other moment in time. There's different forms of energy, and energy can transfer from different forms. So the key is with the conservation of energy, we need to add up all the different forms of energy at one moment in time. And then we know that that's going to be the same total amount of energy, but the energy may have changed form. Units of energy are joules, and then other terms that we'll use related to this: speed, endurance, and strength. Okay, thank you.